Você vai ver quando chega as partes.
So maybe start.
Yeah.
So hi everyone. Today Luca Vitagliano from the University of Salerno is going to talk about contact structures and differential styles. Luca here.
Yes.
Okay.
Yeah.
So please.
Thank you very much. So thank you very much for the invitation, and I really wish I was there. So the program looks very, very interesting. So next time I will come. So I'm having some problems with my tablet, so it might switch off at any time. But in that case, I will just share the screen of my computer. Okay. Today I'm reporting on a joint work with Alfonso Tortorella and Antonio Mario. He is a student with us. And I'm very happy to present the material at this conference because well, we were very much inspired by the work of people based in Brazil, as you will see from my reference list. Okay, there are two keywords in the title. One is differentiable stacks. The other is contact structures. But I believe most of you know both words. But in any case, I have a small introduction on both just in case. So let's begin with differentiable stacks. Well, actually, I will assume that you're familiar with the Lie group points. But if you're not, just stop me and I'll try to explain a little bit better. Okay, so let's begin with Lie group points. So there is this notion of a Morita map of Lie group points. A Lie group point in particular is a group point, so it's a category. So one can consider an equivalence, categorical equivalence between two group points, and a Morita map is basically an equivalence which is additionally smooth, meaning not just smoothness, but also some technicalities which I don't want to discuss. And these Morita maps generate an equivalence relation on the group points, and now with differentiable stacks. There are several definitions, but one which is useful for us is the following: a differentiable stack is just a Morita equivalence class of the group point. There is a very useful characterization of Morita maps by Matias Deloyo that helps us a lot to understand what a differentiable stack really is. So he proves that the Lie group point map F is Morita if and only if it induces a homeomorphism at the level of the orbits on the orbit spaces, and additionally preserves some transverse geometry which is canonically attached by the Lie group point to the orbit space, whatever that means. Well, in other words, we understand the differentiable stack as an orbit space of a Lie group point together with its transverse geometry, whatever that means. In particular, we can understand differentiable stacks as some kind of singular spaces, and that's very useful for our understanding. So for instance, quadrifold leaf spaces of foliations, also orbit spaces of group options, they're all instances of differentiable stacks. Then the question arises: one can really do geometry on these singular spaces, but because of the definition, it's geometry on a Lie group representing it, but we have to guarantee that at every step of geometry for it invariant, so it's really a property of the stack, not just of the Lie group. So in this type, geometry on a differentiable stack is just Morita invariant geometry on Lie groups. And I have to remark that when structures on differentiable stars are actually graded. So they possess a grading which inherited from the grading appearing in the simplicial structure of the nerve of the group point. So we might have like a zero shifted structure, one shifted structure, or even negatively shifted structures, and so on. Among all the possible structures and the shift structures on a differentiable star, the particular interest for people in Poisson geometry are the plus one shifted symplectic structures. So in differential geometry, these were defined or independent by Ping-Shu and Bursting Einstein 20 years ago under different names. So Shu is quasi-symplectic groupoid, Bursting et al. Name is symplectic groupoid. For now, it's enough to tell that these plus one symplectic structures were actually the global counterpart of Dirac structures twisted by Shaw's treatment. Later, I will say a little bit more about these structures. And actually, this is the Morita. One can show that this is the Morita invariant notion. So plus one shifted structure, plus one shifted symplectic structures are actually structures on the top, not just on the group point. The second keywords in my title is contact structures. Let me shortly remind you what the contact structure is. So take a manifold. So contact structure is an hyperplane distribution on the manifold, meaning a codimensional one distribution, which is additionally maximally non-integrable. So what does it mean maximally non-integrable? Well, to every hyperplane distribution, one can attach the curvature. This curvature is a two-form on K with values normal line bundle Tn over K, which is given basically by the commutator of vector fields for the distribution modulo the distribution itself. And it's clear from the definition that this is an abstraction to the involutiveness of the curve of the distribution. And then it's natural to define the distribution to be maximally non-integrable if these two-thirds are non-integrable. That's a contact structure. And this contact geometry is interesting in many respects. First, there are canonical examples. For instance, there is a canonical contact structure on every off-dimensional Euclidean space, also on the projectivized Potankin bundle, and also on the first set bundle of any line bundle. And these structures are relevant in, for instance, time-dependent mechanics or mechanics of fiction, thermodynamics. They're relevant for first-order PDEs. They appear in the quantization of symplectic structures and so on. And well, actually, this contact geometry turns out to be an odd dimensional analog of symplectic geometry in many respects. Well, even more, there is a dictionary that allows you to translate from symplectic and related structures to contact and related structures. So if I will have some time at the end of the talk, I will briefly mention some details about this dictionary. Okay. There is a dual definition of what a contact structure is, which would be more useful for my purposes. Let me discuss it. So, before I begin with the manifold, and I want to begin with the pre-existing line bundle on N. So, N is a line bundle. And I define a contact form to be a one form on M with values in this line bundle satisfy some conditions. Well, first, it's everywhere on zero. In particular, the kernel it's a very well-defined plane distribution. And second, you cannot touch to a one-form at least the curvature, which is again a two-form on the curve with values in the line bundle, which is given by this formula. And we ask to this curvature to be non-degenerate, similar as before. But I have a stupid remark, which will be useful later. Actually, so the curvature of the one form is only defined on the kernel, but actually it can be extended to the whole tangent bundle with the help of a connection in the line bundle. But actually, it's obvious from the formula that the curvature agrees with the restriction to the kernel of the connection differential of the one form. And sometimes this is useful, so I ask you to remember this. Well, this definition is basically equivalent to the previous one. So there is an equivalence of categories between contact form and contact structures, which takes every contact form to the kernel. I should also mention that this terminology is not the usual one in the literature. It's people usually call contact forms plain one form. So one forms with trivial coefficients, not one forms with values in a line bundle. Anyway, I want to stress that there are 5 main aspects in this definition. Well, first of all, there is a line bundle. Second, there is a line bundle valued at one form. Third, there is the kernel of this one form. Fourth, there is the curvature. The curvature, the dimension, is a form on the kernel valued in A, which could actually be also understood as a vector bound map from the kernel to the adjoint kernel. The adjoint is just a simple vector bundle represented by the line bundle. The last aspect, which is the degeneracy, which means that the curvature is an isomorphism in the kernel and the trunk. And well, basically the goal of this talk is goal stacking, right? So I would like to have a stacking definition of what the contact structure is. And to do that, I'll follow the following strategy. I'll go stacking to every single one of those aspects in their order. Before doing that, let me say a few more words about shifted symplectic structures, in particular plus-one shifted structures. So there are several possible definitions. One is the original one by Ping Shu and also the original one by Burstein et al. And there is a more recent equivalent definition by Deloy Ortiz, which will be it was very inspiring for us and would be very useful for the purposes of the talk. So according to this definition, a plus-one shifted symplectic structure on a glucoid is a pair consisting of a 2-form on G and a 3-form on the base. On the base and on the space of object, satisfying certain conditions. But the first condition that omega is equal. For the second condition, we do not ask omega to be closed, but only to be closed up to a homotopy, which is encoded by the 3-form omega. And finally, the 3-form omega satisfies a certain higher coherence condition, which is similar to the higher coherence conditions in infinity algebras. But maybe I should mention that these conditions can be also rephrased in terms of the Bott-Schumann-Tasche bicomplex of the group point. But that's not really important for us. Well, in a sense, this condition replaces the usual d omega equal to 0 condition on symplectic structures, on ordinary symplectic structures. And of course, we also want to replace the non-degeneracy condition, which usually says that the flat map of omega is the non-degenerate, right? But a non-degenerate is a little bit too much because we want the notion to be Morita invariant. So it is enough that this R map is actually just a Morita map. So in some sense, omega is non-degenerate only at one. But it's mentioned already in this one, this is just an omega twisted Dirac structure on M. But what is more important is that with this definition, the notion is actually Morita invariant. So it's actually, so Poisson shift specific structures are really structures on differentiable stuff, not just on the group. Okay. And now we were inspired by this definition to find a contact version of Poisson shifted syntactic structures. As I promised, in order to preserve our definition, I'll go stacking in every single step, in every single aspect of the definition in their order, right? So I want to begin with a line bundle, and I want to go stacking with a line bundle. So I want to have a stacking replacement for what a line bundle is. In order to do this, I need first to recall what a BB groupoid is. A BB groupoid is a groupoid object in the category of vector bundles. It means when we have a diagram whose rows are Lie groupoids, the columns are vector bundles, and everything is compatible. In particular, the Lie groupoid structure maps are all vector bundle maps. If you have a BB groupoid, then you can define a vector bundle N called the curve, which is the kernel of the source map restricted to units. And if you restrict the target of V to the curve, you get a vector bundle map from the curve to the side bundle, which it's usually called the core anchor. And actually, it's a good idea. It turns out that it's a good idea to interpret this core anchor as a two-term cochain complex of vector bundles. In particular, one can take the fiber over a point of the cochain complex, like a cochain complex of vector spaces, which is sometimes called the fiber of the BB groupoid over the point on the base. And the reason for this terminology will be clear a little bit later. But for instance, given a BB groupoid, the tangent bundle is always a BB groupoid over the tangent bundle, and the fiber turns out that the fiber over X just was the anchor map of the Lie algebraic A of the groupoid G. The cotangent bundle of G is also a BB groupoid, this time over the dual of the Lie algebraic, and the fiber is basically it's just the transpose of the fiber of the tangent groupoid. Of course, I would like to go statically, so I would like to make this notion Morita invariant. Well, actually, Morita invariant properties of BB groupoids were studied by the lawyer Ortiz. They first defined BB Morita maps. So BB Morita maps are maps of BB groupoids which are additionally Morita. They generate an equivalence relation, and an equivalence class is called the BB stack. And actually, you should think of a BB stack as a vector bundle over the stack represented by the base groupoid. So as long as we want to work with stack vector bundles, we will actually work with BB stacks in this talk. Okay? Well, what I really want is line bundle. Well, first I need an additional remark, which will be used later, which is again due to the Deloitte. They characterize in a very useful and well, inspiring way the Morita maps. So it turns out that a map of two BP group points is BP Morita if and only if the map on the basis is Morita, and additionally F induces a map between the fibers, which is actually quasi-isomorphism. Well, in other words, we can think of the type of the fiber of the BB groupoid as the fiber of the BB stack over a certain point in the differentiable stack, a certain orbit of the groupoid. So we will adopt this general philosophy that the fiber of the vector bundle in the differentiable stacks is just the only type of the type of the BB groupoid, and this is a very useful way of thinking. As I was mentioning, I actually need line bundles, so I introduced this notion of an LB groupoid, which is just a line bundle in the category of groupoid, meaning that it's a DB groupoid where now both the total, the arrows and object form line bundles over arrows and objects. From this condition, it follows automatically that the curve is trivial, and this is useful because with the curve being trivial, we can conclude that the source, the target, actually all the structure maps on the line bundle groupoid are isomorphisms, and this is useful. Okay, and of course, a line bundle in the stacks is just the BB Morita class of an LB groupoid. And with this definition, we're done with the first aspect. When stacking with the notion of a line bundle. And now, the second aspect, right? So I want to define a static version of a line bundle valued 1/3. So I need a line bundle in its static version, so I begin with the point L, and I will also need the nerve. But the nerve of the total groupoid is actually a vector bundle over the nerve of G, but this is a sequential vector bundle. But what is important here is that all face maps, because the curve is trivial, all the face maps are actually isomorphism on fibers, and this allows you to define a simplicial differential on the line bundle valued differential forms on the nerve of G. So as usual, the simplicial differential is just the alternating sum of the pullback along the face maps. But notice that this pullback is well defined on vector valued forms precisely because these structure maps are isomorphic in fibers. Well, in particular, we have this simplicial cohomology, and we need, well, what we really need is the line bundle form on G, which is, well, first compatible with the grouplet structure. And the nature of compatibility is closeness under the simplicial differential. Actually, we call multiplicative a vector valued form which is closed under the simplicial differential. Well, this definition agrees with the definition of Frank Salazar-Schuchiner in terms of representations of the groupoid. Then we go stacky, and to go stacky, we look at the homology of the simplicial differential. And due to, well, thanks to a theorem of homology is actually Morita invariant. So actually, this homology is really, any such homology class is actually structured on the differentiable stuff. So in other words, a stacky different bundle with different form on our stack is just a cohomology class in this. This way, we basically went with the second object, and how we want to define the kernel of a stacky one form. So again, we begin with a line bundle in group point. We take a multiplicative line bundle variable one form, and we want to define its kernel in a Morita invariant way. Well, in order to do this, we use the interpretation of the homotopy type of the fiber of a VB group point as the fiber of the vector bundle in differentiable stacks. To do this, I need to remark that actually theta can be understood as a VB group point map between the two appropriate VB group points. Well, first, on one side, I have the tangent group point, and on the other side, I have N, but with a new VB group point structure, which is different, which is related to this one, but it's different. Now the side bundle is just the trivial, so this is the trivial vector bundle over 3. And if we understand theta as a vector bundle group point map, like that, it induces the map on fibers. Now the fiber of the tangent group point is the anchor of the large point, as I mentioned. The fiber of this group, the big point, is actually just one term, a very stupid one term cochain complex, and theta is a cochain mount, right? And as I mentioned already, at the level of the stack, only the homotopy type counts. So it's very natural, from this point of view, it's very natural to define the kernel of theta not just as the standard kernel, but as the homotopy kernel of this cochain mount. So the homotopy kernel is basically the shifted mapping clone. So with this in mind, we took the mapping clone of this cochain map, and by degree reasoning, it's a two-term cochain complex, which I denote with this bold K. It will play the role of the kernel of theta we start at the point X. Luckily, it's not just the cochain complex vector spaces or vector bundles. Being a two-term cochain complex candidate to be the fiber of the VB group point. And actually, it turns out that it's not only candidates, it's really the fiber of a VB group point, which I denote like this. So I say more work about this VB group point on this slide. So this VB group point will represent the VB stack corresponding to this VB group point should be really seen as the fraction of the one form theta. So it's important for us, so let's have a closer look at it. So as I mentioned, it's a VB group point over G. So the arrows is just the direct sum of TG and L. The object is just the direct sum of Tn and Ln inside the bundle of my LV group point. But the structure maps are not the direct sum, the structure maps of the direct sum VB group. Actually, they get deformed by theta. For instance, well, I don't want to list all of them, but for instance, the target of the VB group point is given by this formula, where you see theta appears explicitly. So how can we be so sure that this is a good replacement for the kernel. Well, we have a strong indication in the case when theta is everywhere non-zero, then we can take its honest kernel, right? And if we do this by multiplicativity, the kernel is the group point itself. And it turns out, in this case, the embedding of the kernel into the Morita kernel is actually a BB Morita map, so they define the same BB star. And in this sense, this is a good replacement for the kernel of the multiplicative one-fourth. But notice that while this only exists when theta is non-zero, this exists for every multiplicative form, even if the one form is zero somewhere. So while the kernel of the standard one form might not exist as a vector bundle, the kernel of the stacky one form does always exist as a bit star. This is already interesting in itself, in my opinion. Well, first, we need also this notion to be Morita invariant. And it turns out that this is actually Morita invariant in the sense of this theorem. So the BB Morita class of our Morita kernel actually only depend on the BB Morita class of the line bounded group point and the simplicial cohomology class of the one form. And this means that it's actually on the top. We actually consider as the kernel, the static kernel of theta. Okay, and with these we are done with this third aspect. And the next aspect is the curvature. We want to have a static version of the curvature of a hyperplane distribution. So again, we begin with a multiplicative one form. But maybe remember that in the usual case, when theta is the one form on a manifold, also different from zero, that the curvature is a vector bundle map from the kernel to the adjoint kernel, which can be extended to the whole tangent bundle with the help of a connection in the line bundle like this. So the curvature is basically the restriction to the kernel of the connection differential of the one form. So this is, it's useful to remember this remark because it suggests us how to define a static version of the curvature. So of course we need the Morita kernel, and we also need like a version of the adjoint kernel. So we take the adjoint Morita kernel, which is the dual twisted by L, and it turns out this guy is itself a BB group point playing the same role as this one in the realm of group point. The objects are the adjoint of the algebra. So this is as usual, just the dual twisted by the line bound, right? For instance, the fiber is adjoint Morita kernel. It's just the adjoint of the fiber of the Morita kernel. Now I want to define a map from the Morita kernel to its adjoint, which should be a replacement for the curvature. But remember that the Morita kernel is Tg plus L. So whatever these maps should be defined on all tangent vectors G, not just on the kernel of theta. So inspired by this formula, we choose a connection in our line bundle group point. Actually, this can be done in several different ways. For instance, one could begin with a connection in the base line bundle. And then one has even two connections on N, the pullback connection along the target and the source. Here we are using that target and source here are isomorphisms of fibers. So we can take the pullback of the connection here and we get the connection there. We will also need the difference of these two connections. So these are connections in a line bundle. So the difference is actually a honest one form on G, and it turns out that this form is actually multiplicative. So it's closed under the sequential differential. In particular, we can take the sequential homology class, and it turns out that this is an obstruction to the existence of an invariant connection on Ln. But okay, but this is another story. Now, with all these ingredients, I'm ready to define a static version of the curvature as follows. So again, I begin with an LP groupoid, a multiplicative one form, I take the Morita kernel, and then I'm able to define a vector bundle map, which is also a groupoid map between the Morita kernel and the adjoint Morita kernel, which agrees with the connection differential on theta on the TG P.G sector. And then it's given by this one from here, the mixed sector. Well, and it turns out that this is a good replacement of the curvature of theta, which we call the Morita curvature, because it turns out to be Morita invariant. I'll discuss this in a second. In order to convince you that this is a good definition for a static version of the curvature, notice that if theta is non-zero, then this Morita curvature actually boils down to individual curvature at least up to Morita one. And another motivation is that actually this Morita curvature is Morita invariant in the following sense, that it does not depend on the dB part of my line bundle groupoid and the simplicial homology class of the one form, at least up to Morita maps and natural transformations. For instance, if I choose an upper connection, then I get a different definition of the curvature, but the two curvatures are related by a natural isomorphism, and for this reason, they are the same at the level of the stock. Okay, and finally, I can provide the final definition, implementing a static version of the non-degeneracy condition. But now we should be clear how to implement this thanks to the Loy-Ortiz definition of a class one shifted symplectic structure. So inspired by that, I defined a class one shifted contact structure on an LB groupoid as a multiplicative one form with the property that the Morita curvature, well, I don't ask the Morita curvature to be only generate, I only ask it to be only generate up to homotopy, up to Morita equivalence. So in other words, I ask it to be a DB Morita map. Well, for instance, if theta non-zero, that's equivalent saying that the curvature, the plane curvature is a DB and it turns out that this notion is of class one shifted structure is Morita invariant in the following sense that if you have a DB Morita map of two line bundle groupoids, then the pullback along F establishes a bijection between class one shifted contact structures, well, more precisely between the simplicial homology classes of class one shifted contact structure. And in this sense, it's really a structure on the stock. Okay, next I'd like to, so this is our definition. It's Morita invariant and everything works. It's the stacked analog of the definition of the compact structure in some respects, as I mentioned already. Now, to convince you, maybe I need interesting examples, right? Well, the first example was suggested to us by Chen Cheng Zhu. So actually, there is a notion of a pre-quantization of a +1 shifted structure, which is due to Beren's Shu and also Rajan and Shu. And actually, these pre-quantizations provide examples of +1 shifted contact structures, precisely as pre-quantum bundle over symplectic manifolds provide examples of contact manifolds. So in order to give you a little more detail, let me remind you what the pre-quantization means in this setting. So first I need the notion of an S1 central extension over the S1 gerb on the group point. This is just another Lie group point with the same objects with an additional structure of S1 principal bundle over G. Such a way that the principal bundle structure and the group point structure are compatible, so they commute in an appropriate sense. And now, so given a +1 shifted structure on G, a pre-quantization is just an S1 centered function. So this is the original definition in these papers. So it's an S1 centered exposure. A key with two more data, namely a 1 for on H and a 2 for on N with some properties. So theta is actually a principal connection 1 for, which is multiplicative and whose differential agrees with omega, well, the pullback of omega up to a homotopy, which is encoded by kappa, and then there is a higher coherence condition for kappa. The differential must agree with the middle. And we have this proposition that according to the definition, theta is actually a +1 shifted contact structure on H. But actually, this is the +1 shifted contact structure of a particularly simple type, because being a principal connector, this possesses, it really possesses a kernel, and there's no need to use the Morita kernel. But it also suggests that there might be a more general notion of pre-quantization that maybe make them quantizable more +1 shifted symplectic group. But this is just a speculation, and we do not have any indication in this direction. For examples where let me briefly discuss the infinitesimal version of the +1 shifted contact structure. With the infinitesimal versions, and basically we can extract some examples. So let me remind you from the third point that +1 shifted symplectic structures are the global counterparts of Dirac structures twisted by closed treetwork. And actually, there is a perfectly analog statement in contact geometry. So +1 shifted contact structures are actually the global counterparts of Dirac-Jacobi structures. So these Dirac, I don't want to tell you what Dirac-Jacobi structure is, a few words. So they are the contact analogs of Dirac structures. So given a line bundle, so this is a line bundle, you can hook up its gauge algebra with sections or derivations of the line bundle, and also the first jet bundle. if you take this direct sum, then it turns out that this is a Courant algebraic-like object, and then Dirac-Jacobi structures are just Lagrangian subbundled into this Courant-like algebraic, which are additionally involutive in an appropriate sense. And these Dirac-Jacobi structures are interesting because they're very flexible objects. They actually encode several different geometric situations. For instance, Rachmann-motivated one-forms are Dirac-Jacobi structures, but also flat connections in line bundles are instances. When Jacobi structures are examples, when Dirac structures themselves are instances of Dirac-Jacobi structures. Finally, one can generalize complex geometry in odd dimensions using these Dirac-Jacobi structures. And of course, with Dirac-Jacobi structures, we can construct very many examples of plasma shifted complex structure. So just take a Dirac-Jacobi structure. If it's integrable, then on the integrating root point, there is a plasma shifted complex structure. Okay. So far, I discussed +1 shifted complex structures, but as I mentioned, usually geometry are differentiable static shifted, so metric structures as a degree. So far, I considered only degree 1, but actually we can also study degree 0 shifted complex structures, also higher degree. Let me mention a few words about 0 shifted complex structures because they are interesting. In some sense, they're surprisingly more complicated than +1 shifted complex structures. So in order to define this 0 shifted complex structure, I begin again with line bundle group point, and now I take instead of taking one form on G, I take a one form on N. But again, it's compatible with group-like structure in the sense that it's closed under this completion differential. Next, I want to define its kernel, right? In order to have a contact distribution. And now, basically, I begin working on fibers as I did before. Because now theta is a one form on the base, now it can be seen as a cochain map between these two fibers. So this is the fiber of the tangent group point. This is the fiber of M. And for the same reasons as before, as at the level of the stack, only the homotopy type of the fiber counts, it's natural to define the kernel of theta as the homotopy kernel of this cochain map. But now, by degree reasons, the homotopy kernel is actually a 3-term complex. So no chance it to be the fiber of a BB group point. It's a more complicated object, right? But actually, it's not just a 3-term cochain complex. It can be proved that it supports a representation of the homotopy of the Lie group point. So it's a 3-term representation of the homotopy of the Lie group point. And so it's natural to define the kernel of theta as this 3-term representation of the homotopy. We call it again the Morita kernel. We can define the curvature with the atomic connection, and now it's a map of representations of homotopy. Notice that this picture is consistent with the previous one, the one that we had for +1 shifted. The reason is that two terms representations of homotopes are actually equivalent to BB group points times the theorem of Gracia-Salz and Meta. And now 3-term representations of homotopy are equivalent to more complicated objects, which I will not discuss. but I'll just mention it. Being this representation concentrated in both positive and negative degrees, so probably it's the fiber of a higher derived vector bundle in size. Okay. And finally, define the zero shifted contact structures. When imposed to the curvature to be non-degenerate, but only non-degenerate after all. So the natural definition is that the curvature is actually quasi-isomorphism of representation after all. It turns out this notion is more invariant, so it actually notion is flat. For instance, contact structures on orbitals are instances of these zero shift contact structures. So zero shift contact geometry is also interesting. Okay. How much time do I have?
I think you're like 5 minutes. Maybe more. Can you hear me, Luca? Okay. Yeah. No, the sound is really low now for some reason. Maybe it's the problem is here, I don't know. Can you talk?
Yeah, sure.
Yeah, it's good. It's good.
No, it's good. It's back.
Can you hear? No.
Yeah, now.
Yes, we can.
It's back.
Okay. Can I go on?
Yes.
Okay, very good. So, as I mentioned, there is this dictionary that allows you to translate from symplectic to contact geometry. And actually, it turns out that if you apply this dictionary to +1 shifted symplectic structures, you actually get +1 shifted contact structures. And this is yet another motivation for our definition. So let me remind you what does this dictionary work. So I begin with the notion of homogeneous symplectic manifold. This is a principal bundle with structured group, the multiplicative group of all zero fields. So this is just R minus 0 with the multiplication. The principal option is usually called the homogeneity structure. And now an homogeneous symplectic manifold is just the principal bundle with additionally a symplectic structure on its total space, which is homogeneous of degree 1 with respect to the homogeneity. Homogeneous of degree 1 with respect to the homogeneity structure. Homogeneous of degree 1 means this condition. So when I take the pullback along the principal action, I get this thing. And why are these interesting for contact geometry? Because it turns out that there is an equivalence between the category of contact manifolds and contact homomorphisms on one side, and the category of homogeneous symplectic manifolds and the varying symplectic homomorphism on the other. And this equivalence works in this way. Deal with a manifold, a line bundle, and a contact 1/4 on it, then we can contract the homogeneous symplectic manifold, which is sometimes called the symplecticization, in this way. Well, first we take the dual of the lambda, we remove the zero section. If we do this, we get the principal R star bundle. Now we can take the pullback of theta. But sections of the line bundle are basically the same as functions on P, which are homogeneous of degree 1. And in this way, we can understand this pullback as a harmonious 1/4 on P, which is additionally homogeneous of degree 1. and it turns out that its differential, it's actually an homogeneous symplectic structure. And these correspondence can be inverted up to isomorphism and gives this equivalence. So now we have this theorem motivating even further our definition of +1 shifted symplectic structures. We have an equivalence of categories from +1 shifted contact groupoids on one side and homogeneous +1 shifted symplectic groupoids on the other side, which is actually an equivalence up to homotopy. So everything is up to homotopy because we are really interested in the style part of the groupoid. And of course, in order to better explain this, I have to explain what do I mean by homogeneous +1 shifted symplectic groupoid. But it's easy, it's just a groupoid with the +1 shifted symplectic structure with an arbitrary structure of principal bundle R star bundle over base point plus all sorts of compatibilities. And I think that my time is over, so yeah, I think that I can stop here. Thank you very much for your.
Thank you very much, Luca. Are there other questions?
Can I ask?
How
Do you hear me?
I think so.
Okay, can you go back to your definition of one shifted contact?
The definition is different, right?
Yeah. So I was just wondering if, so if I understood, in this case, this line bundle L just comes from an ordinary representation, right? It's just the group acting.
Right.
And this VB Morita condition, you can also phrase as, I think you call this the chord anchor sequences being quasi-isomorphic. I was just wondering if if you could rephrase this in a more, in a more explicit way in terms of things that, I don't know, just to make it more recognizable.
At the level, you mean at the level of the fibers?
Yeah, just to
So at the level of the fibers, let me draw here. So we have a Morita, so we want a Morita mount. We want the curvature to be a Morita mount from the Morita kernel to the adjoint. Actually, this is equivalent to the DP Morita tend to the piece. This is DP Morita if and only if the mapping used on fibers is a quasi-isomorphism. And the mapping used on fibers looks like this. En plus Ln, here you have A, dot, sorry. Here you have, here you have A, here you have this. So this is the fiber. This is the fiber of the Morita kernel. Here you have rho theta, and the fiber of the adjoint Morita kernel is just the adjoint. You have this. And here, basically you have the, whereas you have the connection differential of theta, and here you have the same twist sign. But you can describe it explicitly in terms of this picture, and you want this to be a quasi.
Yeah. So I just wanted to have a look at the definition like this so that I have a better chance of finding it or seeing the examples. I see. Okay, thanks. And just another. Okay, sorry, just as the volume,
Could you repeat, please?
yeah, just that the volume was kind of low again.
Sorry, no, I didn't hear.
I'll get closer to the microphone. Can you hear me?
Yeah.
Yeah, no, thanks for the explanation. I was trying to see. And the other question is about your zero shifted definition. So in the symplectic case, if I'm not mistaken, I think you know that the group point has to be regular, right? Has to be a foliation group point.
Right.
And the
Right.
form has to
So
be
in this
basic.
case,
Yeah, so is there anything similar here?
yeah, so in the symmetric case, the point must be regular.
Yeah.
In this case, it's not needed. So,
Uh-huh.
well, it has a certain regularity, which is not the usual one. But in particular, we have examples where this group point is not regular.
Okay. Okay, thank you.
You're welcome.
Do you hear me, Luca?
Yeah.
I was just wondering, in this shifted symplectic case, you can rephrase moment map conditions by looking at the Lagrangian structures. Have you thought about something similar in this setting by considering Legendrian structures or something like that?
It's in our to-do list, but we didn't have, we haven't looked into that yet. But yeah, so basically this is the PhD thesis of Antonio Maggio, and we are planning also to, well, if we have time, we are planning also to look into this. Yeah, so thank you very much for the comment.
And the other question is in the example of contact or defaults. Even in that case,
yes,
the Morita kernel has 3 terms or something smaller?
Let me think. No, the algebroid, no, in that case, the algebroid is trivial because the group point is étal, so it's really a 2-term. But it's a 2-term which is concentrated in positive degrees instead of negative degrees. So it's really a derived thing, not a static thing, it's a derived thing.
Okay, thanks.
You're welcome. Thank you.
Questions? I think we can take a peek, okay?
pegar para não esquecer.
And then you can write it on the board.
Yeah. There's only one thing. So now, Abertura, Mançur, IMPA, we'll talk about.
Thank you for the invitation. It's our honor to give this talk today. Today we will talk about many triples for double Poisson structures. So we start with some motivation of our problem. The history starts with Poisson-Lie groups and Lie algebras. So Poisson-Lie groups, a Poisson-Lie group is a Lie group with a Poisson structure and some compatibility. In this case, is that the multiplication is by a Poisson map. And a Lie algebra is a Lie algebra, and its dual also has a Lie algebra structure, and we have some compatibility between these two structures. And the important thing here is that these objects are related by differentiation and integration. In this first column, we have many triples. So a many triple is a Lie algebra that we write that as a double of two Lie algebras, and we have non-degenerate, symmetric, and invariant bilinear form. And these two objects are equivalent. So to have a Lie algebra, we can consider the double of these two algebras, and with the canonical bilinear form, and we get a many triple. And if you have a many triple, you can use this bilinear form to identify G2 with the dual of G1, and using the Jacobian invariance, we get that these things form a Lie algebra. The important thing here is that Lie algebras appear a lot of times as many triples. So many triples are important to identify Lie algebras. So we pass to the second line. I spoil it, is that here we will get the global objects. Here you will get the infinitesimal counterpart, and here we will get the double of these things here. Then here you have a Poisson groupoid. A Poisson groupoid generalizes not only Poisson-Lie groups, but also symplectic groupoids, and their infinitesimal counterparts are Lie algebras. And the natural question here is the double of this thing. These were answered by Liu Weinstein-Chu. They showed that this is a algebra with two transversal Dirac structures. Also, this object, this is the counterpart of this object. An interesting thing here is that once we have a Poisson-Lie group, we can integrate it to a symplectic groupoid, and its integration has another groupoid structure and some compatibility between these two structures. So double structures appear even on this line here, so it's natural to consider double structures. So we have the third line. Here you have Poisson double groupoids. Don't worry about the definition of these things. I will talk about this later. A double Lie groupoid was defined by Mackenzie. We have a groupoid over another groupoid and some compatibility between these structures. And in this case, there is a Poisson groupoid. We also have a Poisson structure that is compatible with these two structures in the sense that it is a groupoid. So Mackenzie defined that, but he didn't get around to exploring the infinitesimal versions. So if you pay attention, these structures have two steps differentiations. We can apply the Lie functor on the horizontal direction and also on the vertical direction. This was made by Henrique Bustin, Alejandro Cabrera, and Matias de Hoyo. And they showed that the first differential step of this is our object Lie by algebraic groupoid. The second step of differentiation is our object called a double Lie by algebraic. So I will define these things here, but the important thing here is that we have a compatibility in these two lines that says that this thing with this thing form a Lie by algebraic, and this thing with this thing here form also a Lie by algebraic. And the question that we want to answer is what is the double of these two things here? So by the second line, we have get a Courant algebraic here, and here occurs a similar thing. We have some double, and the answer here is what is the compatibility between these two structures and the compatibility between these two structures. So the guess is that this structure will be a C groupoid, and this structure here will be an LA Courant algebraic. So we'll talk about that. I will talk first about this first line here. We prove this thing, and then we pass to this line here that is harder. We start with some definitions. We start with the definition of a VB groupoid. A VB groupoid is a groupoid over a bundle, and the compatibility here is that the scalar multiplication is by Lie groupoid dimorphism. We have a lot of examples of VB groupoids. Here we have one of them. So if you consider a double vector bundle, and we see one of the bundles as a Lie groupoid, this is a VB groupoid. And when we have a Lie groupoid, the tangent and the cotangent of these things form a VB groupoid. And an interesting thing about VB groupoids is their duality. So when we have a VB groupoid, we have another bundle called core. It's over M. The core is basically the kernel of the source map restricted to the base, to the double base M. And when we have that, we can talk about duality. So if you have a VB groupoid like that, the core is a thing here. We can take the dual on this direction, and you get another VB groupoid. And what if we put a Poisson structure on a VB groupoid? So the compatibility here is that in this side, this is a Poisson groupoid, and on this side, this Poisson structure is linear. So this is the compatibility. And we also have the definition of a Lie groupoid when we have a Lie groupoid over an algebroid. And the compatibility here is that the structures map of this groupoid is by Lie algebraic morphisms. And the interesting thing here is that the duality of VB groupoids says that these two structures are the same. Because here you can take the dual of A on this direction and you get a algebroid. And the compatibility works here. And if you put a Poisson structure here, what do you have? So we have an object like in this way. There we can call a Poisson LA groupoid. And if you consider the dual object of that using this Poisson structure, we get this definition here of a Lie bialgebraic groupoid. So a Lie bialgebraic groupoid, we have two LA groupoids and the compatibility that this thing here with this thing here form a Lie bialgebraic. And this is the object that we want to take the double. So what the double will be. So the guess is that the double will be this structure, a CA groupoid. So a CA groupoid is a Lie groupoid over a Courant algebroid. And what is the compatibility? The compatibility here is more delicate because when we have a double structure with one algebraic structure, we can use the linear Poisson structure associated to define the compatibility. But here we don't do that. So the compatibility here is that the graph of the multiplication of this group, the group right here, is direct on this product. So, and our first theorem is that the Dirichlet double of a Lie bialgebraic groupoid is a multiplicative Courant algebroid. And we have a kind of reciprocal of this theorem that says that when we have a multiplicative many triple, there is G is a multiplicative Courant algebra or equivalent a CA groupoid, and L1 are transversals multiplicative direct structures. So they are transversals. G is the double of this thing, and multiplicative direct means that this is direct and is also a sub-point. So if you have this thing here, we prove that L1 and L2 form a Lie bialgebraic groupoid. And about the proof of these theorems, we use this proposition here that says that if you have a Lie bialgebraic and two bundles, B over N and annihilate of B over N, then they are subalgebraics if and only if the is a direct structure on this double here. And this proposition was made first by Liu Weisstein-Shu, but they do that considering the base B everything. And I did this proposition considering the support. And about the proof, so we have a Lie groupoid algebra, a Lie groupoid bialgebroid, and the double of this thing, and you get something like that. And we want to prove the compatibility between these two things, that is the graph of the multiplication of this groupoid here is Dirac-Ilson product. So the first thing that we do is find a map from this space to this space such that it takes the graph of the multiplication of this groupoid and takes to this double here. So we want to the on the assumptions of the last proposition. So the second thing that I do is find a coherent algebra here that makes this thing here a coherent algebra isomorphism. And this is not the canonical one. So we need to put some signs to our work. And the next thing is to prove that this coherent algebra that we want here is in fact a Drinfeld double of a Lie algebra. So the Lie algebra that we get here is the canonical one, the product of the gamma, but the algebra here have some signals. And then we use gamma and gamma star are LA groupoids. It means that the groupoid structures here are by Lie algebra morphism, so we have that the graph are subalgebraics. And then we get the assumption of the proposition, apply the proposition, and get the results. Here you have an example. So if you have a Poisson groupoid, you have that this tangent and cotangent are LA groupoids, and they are in duality, and this thing with this thing form a Lie algebra. So they are groupoid bialgebraic, and they, if you take the double of them, we get a CA groupoid by our theorems. Now we pass to the second line for the first diagram. So we do the same thing on the infinitesimal case. We start with some definitions again. The first definition is a kind of analog of VB. There is VB algebra. A VB algebra is algebra over a vector bundle, and the compatibility is that the scalar multiplication here is by Lie algebra morphisms. We have a lot of examples of VB algebras. If you have a VB algebra, its tangent is also a VB algebra, and if you have a Poisson vector bundle, the cotangent is also a VB algebra. We do the same thing here, and if you put a Poisson structure here. So we have the definition of a Poisson VB algebra. It's a VB algebra, and the compatibility of the Poisson structure is that in this line, this is a Poisson algebra, and on this line, pi is linear. And we consider an algebra over another algebra. But here, the compatibility is not obvious. But I already had a spoiler about what we do here. Basically, we consider this Poisson structure to define what will be a double Lie algebra. So a double Lie algebra is a double vector bundle with algebra over another algebra, such that when you take the dual on one direction, we get a Poisson VB algebra. So here we have this duality between linear Poisson structures and Lie algebras, and you can do these things to define the compatibility. Now, and if we consider structure here, so we will get something like that. So using the duality between Poisson algebras and Lie algebras, we can find also this structure here, since this is Poisson algebra and this is also a Poisson algebra. So we have the definition of a double Lie algebra. There is two double algebras, and you have that are in duality, and you have the compatibility that this thing with this thing here is a Lie algebra. And this is the object that we can take, that we want to take the double. And how is the guess? So the history in this case is much more difficult because of the definition of a thing called LA Courant algebra. So let's construct this definition. So we have a Lie algebra over a Courant algebra, and we want to define this compatibility here. So the guess is that we can consider the Poisson structure on the dual. So we take the dual on the horizontal direction, and we lose the Lie algebra structure here, and you lose also the Courant algebra here, because since the algebra has a bilinear form, if you take the dual on this direction, we can identify it with its dual. So in this direction here, we don't do that. So what you do to define this compatibility? We know that this thing, pi sharp, is a morphism of triple vector bundles, these triple vector bundles here. And one thing that we want to do is consider that the graph of these things is like hierarchy on something. But here we don't have hierarchy, we don't have Courant structures, Courant algebra structures. So we do is consider the dual of this relation on this direction, and we get a relation from, so do some identifications, we get a relation from TA, from TA to TA. And on TA, we have a algebraic structure given by the lift of this one here. This definition it was made by Leblanc, and the definition it's not a map. I only take the dual on this direction here and get a relation. And this relation will be given by annihilator sharp. Yeah. So we have the definition of an LA Courant algebra that says that basically the compatibility here is that the annihilator sharp of the graph of P sharp is direct on this product. This tangent space we can identify with TA. So we have the same, basically the same Courant algebra structure in these two tangent space. This annihilator here is basically the normal annihilator, but here you have its kind of how things work. So then we get other theory. The first one says that the trivial double of a double Lie algebra is an LA Courant algebra. And a kind of reciprocal says that if you have a main triple, so A is an LA Courant algebra, L1 and L2 are transversals LA Dirac structures. This means that it is Dirac on the Courant direction and a subalgebra on the algebra direction. And then L1 and L2 form a double Lie algebra. And prove that it's harder because the definition of an LA Courant algebra. So, about the proof. We have a double Lie algebra, and we want to take the double of this thing. So, we want to prove that this annihilator here is Dirac on this product. But to prove that directly, put this thing on that proposition is not obvious. So we decide to study what is this thing here. So to do that, we take the simple case when we have a Lie algebra. So if you have a Lie algebra, we can define this relation there is a relation between the tangent space, and you define it by this here. To do that, we need to do some identifications between these tangent space. So the identification here is that we identify this with this, and on this side here, we do this identification here. Here is a map did by Mackenzie. So we do these identifications, and we can define this relation here. The maps that are involved in this relation are that here, and if you consider the graph of this thing, we have a kind of double, and to appear this annihilator, or this relation here, you need to dualize this thing on the vertical direction. When you do that, we get this relation here. That is the same thing that this annihilator here. So if you look at this diagram here, you see that this thing is equal to this thing here. So we will study this relation, and what you do is put other structures on this Lie algebra and watch what happens with this relation. So the first thing is the basic one. When you have a Lie algebra, this relation is a subalgebra over the graph of the anchor. So, and if you have a Lie algebra, this relation will be a triple vector bundle, and we can prove that this face here on the final is a VB algebra. When we have two VB algebras, the relation of the double is the double of the relations. When we have a VB algebra, the relation of the dual is the annihilator sharp on in some direction here of this relation, this original relation. And when we have a double Lie algebra, so let me. So if you have a double Lie algebra, we have here another algebraic structure. So we can consider this relation on the horizontal direction or the vertical direction. So the vertical one over E, and we prove that this thing here is a subalgebra. So using that, we try to put our problem on the assumptions of the proposition. So we have a double algebra and want to prove that is a Dirac structure. So by the last slide, we have that the relation of the double is the double of the relations, and the relation of the dual is the annihilator of the first relation. Also, we prove if we have a double Lie algebra, the relations are subalgebra. So we have also here, we have this. So we apply the proposition and prove that. We have an example. If you have a Poisson algebra, its tangent and tangent are double Lie algebra. In fact, this is a Poisson algebra if and only if this thing here is a double Lie algebra. And these two algebras here forms a Lie bialgebra, you can see here. And if you take the double of these things, we get a Lecourant algebra. So we come to the theorem. An interesting thing of this object is that Enrique, Allen, and Matias prove the differentiation integration relation of this object here with this object here. And by our theorems, we can pass from here to here and come back, and pass from here to here and come back. So we have an integration result that says that are integrated to C groupoids when we have two transversal Dirac structures. And the natural question is, how about the general case is integrated to a C groupoid? And if you differentiate a C groupoid on a Lecourant algebra, and this is an open question that I want to think about. But there is a question in the middle of this thing, because we have this result when we have two Courant algebra with two transversal Dirac structures. And what if we have a Dirac structure and the complement is not Dirac? So we can consider all these things to some objects that we call that double quasi algebraics, and try to do a similar thing and get this result when we have a Dirac structure and the complement is not Dirac. And the first answer is closer to respond this, I think, this question here. So, thank you.
Different definition of transversality. So when you say double transverse, what is it for exactly?
Is that okay? Yeah. So it's like direct sum. Yeah.
Good game. From A star to T.
A star to T. No, but this map is a kind of part of this relation here, because on the other side, so we have this map between this and this, and on the other side, some maps will be the anchor, so will appear something like that.
Right, so how do you count what kind of things that are equal lower?
Lower. So if you have something like that, you are asking like if I consider the relation on the yeah. I know that we prove some things for the algebra, so these things works. But I don't know if you have more things about this relation on down.
The relationship between like the algebroids and representations of homotopy.
Yeah.
When you put more structure on these algebroids, like double the algebroid and stuff, you get more structure on this like representation.
Yeah.
And so in the case of Clavius, there's something like new appearing in this Lecourant algebra.
I don't know. But it is an interesting question.
couple of papers by Mann.
Yeah.
They match up
Where?
she corrects least and canonically.
Yeah.
And then a whole set of crazy equations come out, which are ultimately generalizations of representations of homotopy. So in the case of double the algebroids, it's a kind of matched pair of representations of homotopy. In the case of NA-equivalent algebroids, God knows what they are.
Yeah. But I mean,
But they didn't read the house.
yeah, but does that, I mean, does they study like the global version of that? I mean, it's just
I think that the only thing that I remember, is that is this like breaking up the same way that you take an algebroid and you split it, and then the representation of the homotopy come out. It splits
Yeah.
these other things, and some equations will come out.
Yeah.
And then write it out. See what they are. They look very long and ugly because I think there are a couple of papers that I remember which analyze this makes some sense to them. Maybe one also can remark that even when M is a point, this was treated by so it is generalized. Change on
Yeah,
change.
for by algebras. Yeah.
So there was these for the meeting. And some points for the story, and then everything is much simpler. Right. So we don't have to deal with the compatibility between current algebras and the algebras. It's just another algebra. It's much simpler. Now, it is trying to make sense of how current algebras act with the algebra.
Yeah.